After studying this module, you shall be able to know what are free radicals, learn about their structure, know how radicals are generated, learn the reactivity of radicals. First, let us have an introduction of radicals. The species formed as an intermediate in a chemical reaction which have only one or more unpaired electron are known as free radical. They are often called radical. The unpaired electron is represented by a dot. Life of a radical depends on its stability and conditions of its generation. These species are generally short-lived, extremely short-lived in solution, but can have longer lifetime in crystal lattices of other molecules. Example of some free radicals are hydroxyl radical, oxygen radical, superoxide radical, methyl radical. The free radicals differ from carbocations and carbanions. The valence electrons in a free radical are 7, whereas the positively charged carbon of a carbocation has 6 valence electrons. The negatively charged carbon of a carbanion has 8 valence electrons. So, this radical differs from carbocation and the carbanion being 7 electrons in the carbon bearing radical. Persistent free radicals have a long lifetime and they are resistant to dimerization, disproportionation and other routes to self-annihilation, though they may not be very stable. The triphenyl methyl radical, which was the first radical to be discovered by Gomberg in 1900, although it took 30 more years to know what he had made, it can be generated by the treatment of triphenyl methyl chloride or trityl chloride with silver. The presence of trityl radical in solution can be detected by electron spin resonance ESR. Other examples are 2266 tetramethyl pipridonoxyl radical, that is TEMPO, phenylenyl radical, 1,1-diphenyl 2-picryl hydrazyl radical, DPPH radical. Some examples of stable free radicals are shown. In these cases, the shape and steric hindrance prevents dimerization. The stability may also be increased due to resonance stabilization or delocalization. Next, let us study electron spin resonance or ESR. A radical can be detected spectroscopically using electron spin resonance technique. As an ESR spectrum arises only from species that have one or more unpaired electrons, that is free radicals. This method can be used to detect the presence of radicals and to determine their concentration. Furthermore, information concerning the electron distribution and hence the structure of free radicals can be obtained from the splitting pattern of the ESR spectrum. Electrons have a magnetic moment. When electrons are paired, they have opposite spins which leads to cancelling of their magnetic moments. Such species with paired electron cannot be detected by ESR, but species with unpaired electrons have a net magnetic moment and can be detected by ESR. Certain nuclei have a magnetic moment such as the 1H, 13C, 14N, 19F and 31P. Interaction of the electron with one or more of these nuclei splits the signal arising from the unpaired electron. The number of lines is given by 2Ni plus 1 rule, where I is the nuclear spin quantum number and N is the number of equivalent interacting nuclei. Hyperfine splitting of peaks is observed if the carbon bearing radical is attached to proton due to the interaction of the equivalent hydrogens present with the unpaired electron. For example, the signal for CH radical splits into a doublet. The CH3 radical has 4 lines in its spectrum. Benzene radical C6H6 radical has 7 peaks in the ESR spectrum. Failure to observe ESR spectrum does not prove that radicals are not involved, since the concentration may be too low for direct observation. In such cases, the spin trapping technique can be used. In this technique, a compound is added that is able to combine with the very reactive radicals to produce more persistent radicals that can be observed by ESR. The most important spin trapping compounds are nitroso compounds, which react with radicals to give fairly stable nitroxide radical. Next, let us see generation of free radicals. Now, we will study how free radicals are generated. A free radical is formed during a homolytic bond cleavage such that each generated fragment has one electron with it. Chlorine molecule has 2 electrons shared between the 2 chlorine atoms, and homolytic bond cleavage leads to the formation of 2 chlorine free radicals, each having one unpaired electron from the bond pair. The various ways by which free radicals may be generated are thermal cleavage, photochemical cleavage and decomposition reaction. First, we will study thermal cleavage, how radicals are generated via thermal cleavage. Free radicals may be generated by thermal cleavage. In the gaseous phase, some molecules break down at high temperature. When the molecule contains bonds with 20 to 40 kilocalorie per mole of energy, cleavage can be caused in the liquid phase. For example, the thermal cleavage of azo compound yields free radicals. Azo compounds on heating lose nitrogen molecule and free radicals are generated. Another method for generation of free radicals is the photochemical cleavage. The energy of light of 600 to 300 nanometer is 48 to 96 kilocalorie per mole, which is of the order of magnitude of covalent bond energies. certain molecules undergo homolytic fission in the presence of light of that particular wavelength. For example, the photochemical cleavage of chlorine molecule results into the formation of chlorine free radicals. Next method is the decomposition reaction by which free radicals are generated. At times, a radical molecule may undergo decomposition to form another free radical. For example, decomposition of benzoxyl radical gives phenyl radical and carbon dioxide. Next, let us discuss some features of free radical. A free radical has the following characteristic features. Free radicals are electron deficient species. They are usually uncharged. They contain odd number of electrons. The alkyl radical has 7 electrons around the carbon bearing radical character. In methyl radical or other alkyl radicals, the radical center is trivalent and trigonally hybridized. The carbon is sp2 hybridized in case of free radicals. It has a planar structure. The unpaired electron occupies a 2p atomic orbital of carbon. This singly occupied orbital is often referred as singly occupied molecular orbital SOMO. As stated by Pauli that the two electrons occupying same orbital must have opposite spins and thus magnetic moment of such species becomes zero. However, free radicals have a net magnetic moment. They are paramagnetic due to the presence of one or more unpaired electrons and thus can be detected by electron spin resonance ESR technique. These species are highly reactive due to the presence of unpaired electron which gets paired easily with another electron to fill their outer shell. The alkyl radical have shallow pyramid geometry, that is between sp2 and sp3 hybridization, but the energy required to invert the pyramid is very small. Practically speaking, alkyl radicals are considered sp2 hybridized. The order of splitability of alkyl radicals is tertiary alkyl radical greater than secondary and least is primary, and then methyl radical much less stable. Now let us discuss the stability of a free radical. Since bond dissociation energies give us an idea of the ease with which free radicals can form, they can also give us an idea of the stability of those radicals once they have formed. The lower the bond dissociation energy, the higher will be the stability. Alkyl radicals are stabilized by adjacent lone pair bearing heteroatoms and by the pi bonds. The various factors responsible for the stability of free radicals are inductive effect, hyperconjugative effect and resonance effect. First, we will discuss how inductive effect affect the stability of a free radical. Greater the number of alkyl groups attached to the free radical carbon center, more will be the stability of the radical. This is due to the electron donating inductive effect of the alkyl groups, which decreases the electron deficiency of the radical. The bond dissociation energies of the CH bonds for the formation of a free radical of methane, ethane and other alkanes clearly show that radical centers are stabilized by the replacement of 1, 2 or 3 of the hydrogens of the methyl radical by alkyl groups. For example, the bond dissociation energy of ethane is 98 kilocalorie per mole is less than methane, which is 105 kilocalorie per mole. Thus, the order of stability is tertiary alkyl radical much greater than secondary and then primary, and the methyl free radical is the least stable. So, this stability order can be explained on the basis of the electron donating plus I inductive effect of the alkyl groups attached. Another factor which decides the stability of a free radical is hyperconjugation. Hyperconjugative effect also give stability to free radicals as in the case of carbocations. The stability order of alkyl free radicals is tertiary greater than secondary, which in turn is greater than primary, and methyl radical is least stable. This stability order can also be explained by hyperconjugation effect, as we have explained it on the basis of their inductive effect previously. The odd electron in the alkyl radical is delocalized onto the beta hydrogens through hyperconjugation, which confer stability to the radical. Thus, tertiary butyl radical is much more stable than secondary butyl radical, which in turn more stable than N-butyl radical, as tertiary butyl radical has 3 methyl groups or 9 beta hydrogens, which give it 9 hyperconjugative structures. Secondary butyl radical has 6 and N-butyl radical has 3 hyperconjugative structures. Greater the number of hyperconjugative structures, more will be the stability of the radical. Therefore, the order of stability is tertiary radical, then secondary radical, then primary radical, and the least stable being the methyl radical. Here you can see a methyl radical has single resonance structure. The odd electron is localized on carbon and no hyperconjugative stabilization is seen in case of methyl radical. Whereas in case of ethyl radical, 2 resonance structures are shown here and the odd electron delocalized onto the beta hydrogen. Hyperconjugative resonance stabilization can be seen in case of ethyl radical. Similar hyperconjugative structures can be drawn for other alkyl radicals. Next factor which governs the stability of a free radical is the resonance effect. In the free radical where the carbon center is in conjugation to a double bond, the resonance effect leads to stabilization of these molecules. The stabilizing effect of phenyl groups in allyl radicals and phenyl group in benzyl radicals is very significant and can be satisfactorily explained by resonance. Allyl and benzyl free radicals are more stable than alkyl free radicals, but still have only a transient existence under ordinary conditions. Here we can say the resonance in allyl free radical, there are 2 such structures, and resonance in benzyl free radicals. Now we move to the reactions shown by free radicals, or the reaction in which the free radical formation occurs. A free radical may undergo the following types of reactions. First is the abstraction of another atom or group. For example, halogenation of alkanes proceed via free radical mechanism. The chlorination of methane is shown. Methane, when reacts with chlorine in presence of light, can form methyl chloride, dichloromethane, trichloromethane and tetrachloromethane. This is a free radical reaction. The mechanism involves formation of free radicals. This reaction involves three main steps. First is the initiation, second step is propagation, and third step is chain termination step. In the initiation step, the first step, free radicals required for the reaction are generated in situ by irradiation or heating of the reagent, or by carrying out the reaction in the presence of an initiator like peroxides. The process is always endothermic. The first step is initiation, which involves bond dissociation in chlorine molecule. The bond dissociation energy of the chlorine molecule is 58 kilocalorie per mole. So, chlorine readily undergoes a homolytic bond dissociation. Chlorine in presence of heat or light gives two chlorine free radicals. Next step is the chain propagation step. In this step, the highly reactive chlorine radicals with unpaired electron reacts further. They are electrophilic, thus each seeks an electron to complete its unfilled shell of electrons. In a reaction with methane, a chlorine atom readily removes a hydrogen from the methane. Free radical chain reaction works best when all propagation steps are exothermic. Here, the chlorine free radicals react with methane and homolytic fission between the carbon-hydrogen bond occurs to give methyl radical and HCl molecule. The resulting methyl radical, which also is very electrophilic, then removes a chlorine atom from a chlorine molecule. The final step is the chain termination step, in which two reactive radicals combine together, such as a chlorine free radical may combine with a methyl free radical to form methyl chloride. Two methyl free radicals can combine to form ethane molecule. Two chlorine free radicals can combine to form chlorine molecule. Addition to multiple bonds also involve free radical formation. For example, the addition of HBr to alkenes. The anti-Markovnikov addition of HBr to alkene was probably the first free radical addition reaction to be discovered. Addition of HBr to 2-methylpropane in the presence of a peroxide like ROOR, example tertiary butyl peroxide or benzoyl peroxide, regiospecifically yields 1-bromo-2-methylpropane, which is the anti-Markovnikov addition product. Here you can see isopropane reacts with HBr in presence of peroxide to give a regiospecific anti-Markovnikov addition product. The mechanism proceeds in various steps. The first step is the initiation step, in which the benzoyl peroxide dissociates to give the free radical. That free radical then leads to homolytic cleavage in HBr to form bromine free radical. In the next step, the bromine free radical reacts with the alkene molecule to form an alkyl free radical, and this can happen in two ways, and the radical which is more substituted is more stable. So here a tertiary radical is generated. This radical further reacts with HBr to form the alkyl halide along with formation of bromine free radical, which further propagates the reaction. Another example is the addition of CCl4 across the double bond of norbornene, that is bicyclo-2,2,1-heptene. CCl4 gives CCl3 radical. That CCl3 radicals can react with norbornenyl to form a compound with 75% trans isomer and only 4% of the cis isomer. Rearrangement reactions are another type of reactions which involve free radical formation. Free radicals may also undergo rearrangement to form a more stable radical and then the final product. Radical reduction. In a radical reduction reaction, hydrogen is added to a pi bond. For example, the radical reduction of alkyne to alkene with sodium ammonia is a trans addition of hydrogen to an alkyne. This reaction occurs via the formation of radicals. Another example of this type of radical reduction is the Birch reduction. As shown here, the benzene is reduced to 1,4-cyclohexadiene in the presence of sodium ethanol in ammonia. Now we will study the mechanism of Birch reduction. From the mechanism, it is clear that sodium radical is involved in the reduction, which also forms some other carbon radicals as intermediate in the whole process. So the sodium radical formed after loss of an electron from the metallic sodium reacts with benzene to form a radical and anion. The anion, that is the carbon carrying negative charge, abstract a proton from the solvent ethanol molecule, and the radical again accepts an electron from sodium radical to form a negative charge carbon center at the other part of the benzene nucleus, and this further abstract a proton from ethanol and hexadiene molecule is generated. Next is the free radical polymerization of alkenes. Polymerization may also occur via generation of free radicals. The most important free radical chain reaction is the free radical polymerization of ethylene to polyethylene. Industrially, tertiary butyl peroxide is used as an initiator. The tertiary butoxide radical adds to ethene to give the beginning of a polymer chain. The propagation part has only one step: the addition of an alkyl radical at the end of the growing polymer to ethylene to give a new alkyl radical at the end of a longer polymer. The termination step are the usual radical combination and disproportionation reaction. So overall, when ethene polymerizes in presence of a peroxide, it gives polyethylene. Initiation involves homolytic cleavage in tertiary butyl peroxide to give tertiary butoxyl free radical. This tertiary butoxide radical reacts with ethene to generate our alkyl radical. That alkyl radical further propagates the chain by reacting with another ethene molecule. This is how the polymerization occurs in ethene. Another example of polymerization is the polymerization of styrene to polystyrene, which can also occur via free radical mechanism. The next type of reactions which involve free radical formation are the allylic bromination reaction. Alkenes can be brominated in the allylic position using N-bromosuccinamide, that is NBS. The reaction is known as Wool-Ziegler reaction. A mechanism for allylic bromination by NBS is the bromine in this process is formed in a side reaction between HBr and NBS. The function of N-bromosuccinimide is to provide a low constant concentration of bromine and to use up the HBr formed during the propagation step. So, the NBS undergoes homolytic cleavage between the nitrogen and bromine, and a free radical is generated, bromine free radical, which reacts with the allylic position of an alkene, and that allyl radical further reacts with HBr. The allyl free radical generated is the more stable radical in this case, and this reacts with bromine molecule to form the bromo derivative. Ozone formation and ozone depletion also involve free radical formation. The ultraviolet radiations, if reach Earth's surface, damage plants and animal life. The ozone layer prevents these harmful UV rays from reaching Earth's surface. Now, let us see how ozone formation occurs. Ozone is formed when the ultraviolet radiation acts upon molecular oxygen. Ozone formation involves homolytic bond dissociation in molecular oxygen in the presence of UV radiation, and atomic oxygen radicals are generated. Further, in the presence of ultraviolet radiation, the oxygen radical react with another oxygen molecule to produce ozone. So, the reaction can be represented as O2 plus O radical giving O3. Ultraviolet radiation also dissociate molecules of ozone to produce an electronically excited oxygen atom and an oxygen molecule. Here the reaction is O3 giving O2 plus oxygen radical. These reactions make up a chain reaction that continue as long as oxygen and UV radiation are available. The net result of these reactions is the absorption of most of the incoming ultraviolet radiation and formation of ozone. Now, let us see how ozone depletion occurs. Chlorofluorocarbons CFCs, CFCl3 and CF2Cl2 are widely used as refrigerant, which absorb radiation at the same wavelength as molecular oxygen and ozone. When these chlorofluorocarbons absorb UV radiation, a carbon-chlorine bond cleaves homolytically to form chlorine radical. So, CFCl3 in presence of ultraviolet light forms CFCl2 radical plus chlorine free radical. The CF2Cl2 can also dissociate in presence of UV radiation to CF2Cl radical and chlorine radical. Once formed, the chlorine radical can react with ozone to produce ClO and molecular oxygen. The ClO in turn reacts with oxygen radical to form a chlorine radical and a molecule of oxygen. The net result is a catalytic cycle that destroys a molecule of ozone while regenerating the chlorine radical. This is how ozone layer gets depleted due to chlorofluorocarbons. Next type of reactions in which free radicals are involved are the auto-oxidation reaction. The spontaneous oxidation of organic molecules in the presence of oxygen is called auto-oxidation. Ether solvents undergo auto-oxidation so readily that if stored for a long time, oxidize to form some amount of hydroperoxide products. Hydroperoxide products are unstable and decompose violently when heated. So diethyl ether in presence of oxygen gives hydroperoxide of diethyl ether. The mechanism for the auto-oxidation involves abstraction of a hydrogen from the carbon bearing the ether oxygen by an oxygen molecule. It leads to the formation of a radical and a hydroperoxide radical. These two radicals then react with each other to form ether hydroperoxide. Similarly, furan also undergoes auto-oxidation to form explosive peroxide. Synthetic antioxidants such as BHT are added to packaged and prepared food to prevent oxidation and spoilage. Vitamin E and BHT are radical inhibitors, so they terminate radical mechanism by reacting with radical. The main causes of food spoilage are microorganisms and auto-oxidation. Antioxidants such as butylated hydroxyanisole BHA and butylated hydroxytoluene BHT are added to the food or packaging material to prevent their auto-oxidation. Now we will summarize what we have learned till now. We have learned that free radicals have unpaired electrons and have a planar trigonal geometry where the carbon bearing free radical is sp2 hybridized. N-bromosuccinimide is an excellent source of bromine in low concentration for allylic bromination. Benzylic and allylic radicals readily form because both are resonance stabilized. The halogenation of an alkane is a radical chain reaction. The anti-Markovnik of addition of HBr proceeds via a radical intermediate.